That'd be perfect.
Oh, Jackson, you better be careful.
Be careful. That's right. Watch out. All right. So today we are talking about Chapter 13, Kinetics. The first half of this lecture is very much review, where the second half is new stuff with rate laws and how to determine rate laws. There's a lot of math. So, yay. Just because I am recording, letting you know that we are going to do lecture in 2, maybe 2.5 days and start lab this week so that we can get through that. All right, so at the beginning of this lecture, you're going to be able to describe what a chemical reaction is in terms of mechanism, bonds broken, and bonds formed. Yep. Calculate the change in energy of a reaction and identify our reaction as endothermic or exothermic. Describe the relationships between activation rate and energy and reaction rate. We're going to be able to sketch a reaction energy profile, which hopefully this is review for you. Describe what a catalyst is and how it affects reaction rate. We are going to describe in words and mathematically what factors affect reaction rates, and we will be able to understand the meaning of reaction orders in a rate law. You will last but not least be able to determine reaction orders from a set of data, and then be able to appoint those into the rate law equation. So that one's a fun one. Go ahead and there you go.
Is there going to be another test in the final, or is our last test the final?
You'll have one more test. Yep. All right. So, remember that in when I very first taught you about chemical reactions, I said these are the reactants and these are the products, and we draw an arrow in between, and that is an indicator of produce or yields. And back then I told you right then that that was just the model, and that although we have reactants on one side and we have products on the other side, there are a variety of steps that a lot of reactions go through to get from one side to the other. Whichever of those steps is the slowest is the one that determines the rate of the reaction. So a rate is something that we measure. An example of a rate would be miles per hour. It's posted 55 miles an hour on highways in Indiana. Some people think that is a suggestion, but that is the rate at which your car is supposed to be traveling, the maximum rate your car is supposed to be traveling. Another example of a rate would be like beats per minute. So if you have ever like played an instrument, like a piano, and you've like used the metronome where it and you can set that metronome on beats per minute. All songs typically have a beats per minute. I do lights at church, and we have like different effects or whatever. And one of the things you can do, like when you have a song, is you can like look it up and it'll tell you how many beats per minute it is. So you can set the effects to the lights to change at the same like beats per minute as the song. Those are all rates. So when we talk about the rate of chemical kinetics, we're talking about the rate of reaction, how quickly that reaction happens over time. So the sequence of steps that these undergo while changing from reactants to products is what we are looking at. This is called the reaction mechanism. So there is a sequence of steps typically that happen. We can't see that because we're looking at molecules and atoms. All we see is reactants and we see products. But what we can do is determine how quickly those steps are happening. So when we are talking about chemical kinetics, what we're actually talking about when we look at like a methane molecule and an oxygen molecule, and we're saying how likely is it that a molecule of methane and 2 molecules of oxygen are going to collide with enough energy and in the correct orientation to break the bonds for the 4 carbon hydrogen bonds and the 2 oxygen double bonds. What is that? And that's what our rate is. That's what we're actually looking at. Why is this important? So rates of reactions are incredibly important to all different kinds of things in our world. This is an example of a catalytic converter. This is on a car. I know nothing about a catalytic converter, but I know that it changes the rate of reactions so that we can use it. Here is a picture of a medication. Why does it matter? Medication. Why does the rate of reaction of a medication matter if you take medicine?
So you don't overdose and take too many in a certain amount of time.
Right. So typically, medication that we take is slow release. It releases over time so that that medication stays constant within your body. Like when they tell you, hey, you need to take this antibiotic and you're going to take it at the same time for 10 days, take it twice a day, you take it 12 hours apart so that that medication stays steady in your body the whole time. Birth control is a great example of something that's supposed to be taken at the same time every day to make sure that your hormone levels don't dip and you accidentally get pregnant. So making sure that those medications are slow release over lots of time. Another example is food. Typically, we cook our food fairly quickly. I mean, anything that takes more than 20 minutes is like, all right, seriously. I mean, I know people use a slow cooker and things like that, but most of the time we cook food pretty quickly. But once we eat that food, the reaction rate in our stomach is quite a bit slower. When you eat food, it will sit in your stomach for hours and hours. Why is that? Yeah, you're digesting it. Why doesn't it want to just do it like all at once, like really fast? There you go. It takes time for your body to absorb the nutrients. Also, how much would that stink if you ate it within like 5 minutes? You're like, wow, I feel like I'm empty. I'm hungry again. Yeah, we don't want to do that, right? So it takes time. Here's an example. This is pretty cool, actually. This is a 40, I think it says 43-hour salt test. So they took this piece of metal and they submerged it in salt without any protection on it, and you could see the corrosion on it. And then they used 4 different types of corrosion preventing things on it and did the exact same thing. You can see that obviously that one is the best. It doesn't have very little corrosion on it. So we don't want corrosion to happen on our, like for example, our cars. We would really prefer that not to happen. So we want to slow those rates of reaction down. Why do we put food in the fridge? Caleb?
Because it's colder, so they won't be reacting as quickly.
There you go. It is colder. Guess what? Temperature is one of the things that affect the rate of reactions. So when we lower the temperature, we lower the rate of reaction. So we don't always want things to go immediately and quickly. We want to be able to alter the reaction rates. Okay, so how do we determine the rates if we can't even see them at the molecular level? What we're going to do is we are going to study the speed of reactions by varying the temperature and or the concentration of reactants. This is what you guys are going to do in lab. It's called the iodine clock. And you are going to vary the temperature. Huh? No, that's a Galilean thermometer. Nice try. The iodine clock, you're going to vary the temperature and you are going to vary the concentration of the reactants and measure the rate of reaction. Yeah. Okay, so new type of reaction that we need to talk about is a substitution reaction. So a substitution reaction is when one particle replaces another in a reaction. The example here that you see is the hydroxide coming in to the CH3, and it is kicking the bromine off so that the hydroxide is now attached to the CH3 and the bromine is by itself. This is a substitution reaction. It can happen with any size of molecule on another molecule. So it's the reason it's not called a single replacement reaction is because when we talk about single replacement reaction, that's only one atom. But in these substitution reactions, we're taking one compound and we are substituting it in place of another compound. Also, I'd like you to notice how the orientation of the CH3 changed. Bromine is a negatively charged ion and hydrogens are positively charged. Also, hydroxide is negatively charged. So when the hydroxide moves in to the CH3 molecules, notice that the hydrogen shifted to the other side to be as far away from that molecule as possible. So we still have a polar molecule with a partially negative end and a partially positive end, just like this was polar. They do shift, though, away from the others. All right, so chemical reactions normally exhibit a net change in energy. Energy can be released or energy can be absorbed. Energy can be released in several different forms, including light and heat. This is nitroglycerin. You can see what type of reaction is this, Will? Good job. Both. Yeah, combustion and decomposition. Good job, Will. Does anybody know what nitroglycerin is?
Using dynamite.
It is dynamite. Good job. Nitroglycerin was discovered in the 1860s by Alfred Nobel. From the money that he made from selling dynamite, he founded the Nobel Prize. I don't know if you've ever heard of it, but it's like the prizes that are given out to the scientific community. He discovered nitroglycerin. So nitroglycerin is used in dynamite. Noticeably, when you see the word TNT, typically it's in a solid form. So most of the time, if you see dynamite that is going to be moved or transported, it comes in a stick, like with a fuse on it, right? But nitroglycerin actually is a liquid, and if you have it in the liquid form, even dropping it can cause it to go off. So it's actually a really dangerous compound that you have to be really careful with. Nitroglycerin is also used in heart medication. It also dilates the valves for people who have valve constriction. So because it gives off energy. Yep.
So you're able to consume something, right, and it helps you, but at the same time it also you can blow it up. Yeah. Does that decay it at all, or is it the same, literally the same substance?
No, they're just, yes, they have to change it. So they have different additives. They can add nitroglycerin to different things to be used in medication. Same thing for TNT. TNT is just not, dynamite is not pure nitroglycerin. It's added to something to make it into a solid. Yep, good question. All right, so you know that energy can be released or absorbed by a chemical reaction. So, Haley, what's it called when energy is released? What type?
Exothermic.
Good job. And what's the opposite of that?
Endothermic.
Endothermic, when energy is absorbed. So one of the things that you guys need to be able to do as a class is if you see a chemical reaction that has energy on it, if the energy is included on the product side, that tells you it's exothermic. If the energy is included on the reactant side, that tells you that the equation or the reaction is endothermic. So product side is endothermic, reaction side is endothermic, product side is exothermic, depending on which side it goes on. I know that last year we had a couple questions where it showed this is all you got. It didn't even say nitroglycerin, and it wasn't this reaction, and it just had the energy on the side, and it said identify if this is an endothermic, exothermic, or energy neutral reaction. So you needed to be able to know just by looking at the where the energy was. An energy neutral reaction neither absorbs nor releases energy, so that means that the energy stays the same on both sides of the equation. Anybody got questions on that one? All right, so energy changes. So looking at our diagrams for our energy reaction profiles. We have two different types of diagrams. We have an endothermic and an exothermic. You also need to be able to identify which type of reaction it is just by looking at the picture. So the one on the left is our exothermic reaction, where we start with a high amount of energy and our products have a low amount of energy, so energy is given off. Now, when we look at these types of profiles, we are looking also at the change of energy in the reaction. So anytime you see, anytime you see this delta here, this delta always symbolizes change. So when we're looking at the net energy, the change in the reaction, so we are looking at the change from the reactants to the products. This is our change in energy. Now, the change in energy for an exothermic reaction is always negative. And the change in energy on an endothermic reaction is always positive. So another way to determine endothermic or exothermic is the sign on the change in energy. If it gives you a positive sign for change in energy, you're going to know it's endothermic. If it tells you it's a negative sign on your change in energy, it's going to be exothermic. So far we have 3 different ways to determine rates of or types of if it's an endothermic or exothermic reaction. You should be able to identify it based on where the energy is placed in the equation. You should be able to identify it by looking at a energy profile like this. And thirdly, you should be able to identify it based on the sign of our change in energy. Yes? We're good? Perfect. Okay, so hopefully you know by now that chemical bonds store potential energy. Anytime you have a chemical bond, there's potential energy stored in that bond. And when we break that bond, we have to input energy to break the bond, right? It's an input of energy to break bonds. That means when bonds are formed, what happens? Aaron? Other way. There you go. When bonds are broken, energy is absorbed. When bonds are formed, energy is released. It is given off, okay? So the forming bond is going to release energy to our surroundings. So when we're looking at the relationship between the magnitudes, when we're looking at the quantitative amounts of energy, if it's a large amount of energy that it takes to break the bonds, and then a small amount of energy is given off, this is going to be an endothermic reaction. More energy is needed. We have to put energy in to break those bonds. The opposite is also true. If it's a less amount of energy to break the bonds and there's a lot of energy given off when the bonds are formed, this is going to be an exothermic reaction. So wherever the energy is on which side, that tells you if we have endothermic or exothermic based on the amount of energy needed. It's really, I know 100% there is going to be a question that says something about energy and bond formation. Bond formation, energy is released. When you hear that question, think of these pictures. Think of the making the bond and seeing the energy come off, because that, I don't know why, but that question, I don't know why it throws people off, but maybe it seems opposite, but that is what happens when bonds, energy is absorbed to break bonds and released when bonds are formed. Questions on this slide? Perfect. Okay, so let's look at this energy profile that is not attached yet. I will go ahead and draw the line here. Garrett, is this an endothermic or exothermic reaction? It is an exothermic reaction. Is this container going to feel hot or cold to the touch, Julia? Why? It's going to be hot because it's giving off energy. It is losing energy. You're right. It's losing energy. It's giving it off. Yep, hot. So what is the value of the change in energy, including the sign? Caleb?
Oh, the changes from start to finish? 40.
Including the sign? It is 40. Negative 40 kilojoules, because it is a loss of energy. We are losing energy. Energy is being given off. So he looked at 50 kilojoules here, 18 kilojoules for our reactants, and he looked at the difference between those. So the equation for this is energy of reactants minus the energy of the products gives us the energy, change in energy for the reaction. So you always take your products. Nope, I wrote that wrong. I'm sorry. Products minus reactants. I apologize. So which contains more energy, the reactants or the products? Mason? Products. Does the reaction go uphill or downhill in energy? Maggie?
Why does the product contain more energy?
Yep, you're right. What should it be? Your reactants contain more energy. I wasn't paying attention. Because your reactants have 58. How much do your products have, Mason? How much energy does your product have? Look at the graph. Here's your product right here. 18. There we go. All right, Maggie, back to you. Does the reaction go uphill or downhill in energy? Downhill. Good job. And what is the change in energy if it was the reverse reaction, Cameron? Say it again. Yep, plus 40 kilojoules. If we were going the opposite direction from B to A. Questions on this slide? Yep.
You have to include the plus sign on the 40 kilojoules.
You always do when it's asking typically on, you don't have to. I always do when I'm talking about change in energy, only because that is what determines endothermic or exothermic, and I'm trying to make it very clear where we're at. Anyone else? Okay, so of the three reaction types, exothermic, endothermic, or energy neutral, which do you think is fastest? Talk at your table. Go. Andrew Smith, okay, a little more attention to that.
I don't know. What's the energy of the first set of bonds in there? Or could it be no, it makes what you're saying. So more efforts, but I'm thinking that once you break that first, I could be wrong though. Then the energy release from that bond has to be all bonds around it, and then it'll just be an extra.
Like if I was cooking something.
I'm saying so.
All right, who wants to volunteer their answer? All right.
D because it kind of turns into temperature.
Very good. It is D. None of them is faster than the other. It is temperature and concentration dependent. Good job. Okay, so next part, activation energy. We talked about this last year. This is the energy that must be overcome for a reaction to move forward. It's shown as a peak in the reaction profile. So when you look at your activation energy, we are looking from where our energy starts for our reactants, which is this little dotted line here, and all the way up to the peak. This change here is our activation energy. If a reaction only has this much energy, it will not go. It has to have enough energy to reach the peak to be able to move forward. The other thing that we need to know on this little reaction profile here is our transition state. And we see this right at the top of the peak, and this is where our reactants are changing into products. This is where the bonds are being broken and new bonds are being formed. This is up here at the top. And that is our transition state up here at the top of our energy barrier. So the magnitude of the activation energy matters. If that activation energy is high, it's going to give you a slow reaction. The reason for that is we have to input enough energy for those molecules to reach that point, and sometimes it just takes more time to build up that much energy. If the activation energy is small, that reaction will go quickly because it is a very small amount of energy that has to be obtained to make the reaction go. So the type of question that you might see for something to do with that would look something like this. Which of the following reactions would be expected to proceed faster? Andrew Boyd, which one's going to go faster, A or B? A, why? Good job. I don't think I even knew that word. So because the activation energy is smaller, like Andrew says, the apex of the graph is not the same. It takes more energy to go. So imagine it's climbing a fence or a mountain. A very small hill isn't going to take much energy, but if you have to climb a mountain, that's going to take a lot of energy to get to the top. And these reactions cannot go until they have reached that peak. All right, so here are some data for 3 hypothetical reactions. For each of these reactions, I want you to sketch the profile, determine if it's endothermic or exothermic, and then find the change of energy in the reaction and the change in, and the activation energy. Go. We're gonna do it together. So I'll look at it.
What's 10 minus 1 plus 10? I think just tagging it out 1 star. On what? He's rank 7 though, so it's acceptable, I guess, right? Yeah. Try that. Flyers. Nice.
All right. Okay, in order. 1, 2, 3. Endothermic or exothermic? Number 1?
You're asking me, right?
Yep.
Yeah, I would say exothermic.
No. The reactants are less energy. No, yeah. What did you say? No, it's endothermic. It is absorbing energy. The reactants have less energy than the products. Okay. Dylan, what about reaction 2? Endothermic or exothermic? Exothermic. Our products have less energy than our reactants. What about reaction 3, Julia? Yep. Endothermic. There we go. So what is our delta E of the reaction? Garrett, 1. Plus 10. How about reaction 2? Cameron?
That is 7. From 10, negative 10. Sorry.
It's okay. Will, reaction 3. Plus 10. All right. Energy of activation for reaction 1. Dylan? Kerrigan, reaction 2.
70.
Reaction 3, Lexi? 80. Was it 80? Good job. All right. Do any of you have any questions on these graphs? Perfect. Okay, so there are 3 things that affect if a reaction will occur, and there are also things that we talk about that happen that change how quickly or how fast a reaction will occur. So for a reaction to occur, number 1, those reactants must collide. So they have to run into each other. Anything that is in the solid form typically isn't going to have a reaction. Like if you put 2 solids together, most of the time there's no reaction. That's because they aren't moving very much and they're not going to run into each other. So number 1, they have to collide. Number 2, the molecules must be in the correct orientation for the bond rearrangement to occur. They can't just hit on one side and bounce off. So they have to hit in the correct spot for the bond rearrangement to occur. Number 3, they have to hit with enough energy to break the old bonds and allow the new bonds to form. This amount of energy that they have to hit with is the same as the activation energy. They have to hit with enough energy to make those bonds, break the old bonds and allow new bonds to form. So we've got collisions, correct orientation, and energy. And if they ask you, well, how much energy do they need to collide with? They need to collide with the amount of energy that is the same as the activation energy. If you had an energy profile and you have a chemical sentence, and the question is, how much energy do they need to collide with? When you look at your energy profile and you determine your activation energy, you're able to answer that type of question. They have to collide with the same amount of energy that's your activation energy. All right, so we do have factors that affect how fast a reaction occurs. There are 4 of them. 1 is temperature, 2 is concentration, 3 is the nature of our products, and 4 is the presence of a catalyst. So we're going to go over each of these 4 that affect the rate of reactions. This is what we're going to be doing in our lab, is the rate of reaction. Yep.
Is it possible for any instance for 2 solids to collide? The molecules of 2 solids to collide?
Maybe. Yeah.
How? Like,
One is moving at a high speed, and when it collides with the other, it causes enough movement for them to be able to overcome that activation energy. Right?
have we done that? Like, as we raise up, okay, 2 solids on purpose collide and have the reactive molecules. That's great. How fast do you do that?
Depends on the nature of the product and the orientation that they need to be in.
Yeah.
Anybody else? Okay, so what happens to our particles what happens to the kinetic energy of our particles when we increase temperature? It speeds up. Yes, our particles are moving at a faster rate. Here's an example of a glow stick. You guys all know that to activate a glow stick, you like crack it, right? Whatever, it's got something in the inside that is in a capsule. And when you break that capsule and those 2 things are able to mix and collide and have motion, then you start to see a reaction. Here's an example of a glow stick. One is in hot water and one is in something with the lower ice water. And you notice that the reaction is brighter in the high temperature water than in the ice water. So anybody, well, you guys don't have kids, but when my kids are little and they would have like a glow like necklace, they'd be like, can we put it in the freezer? And we put it in the freezer to try to stop the reaction. So then when it came back out of the freezer, the glow would, then the reaction would go again and it would still work even after. Because usually once they sit overnight, they're toast. So temperature has an effect on reaction rate. Temperature is a measure of the kinetic average energy, the average kinetic energy of the particles. I'm going to say that again. When you are measuring temperature, what you are actually measuring is the kinetic motion of the particles. That's crazy. So temperature is the kinetic motion of the particles. The higher the temperature, the faster our particles are moving, and the more collisions that occur. It's just like a car. People who drive really slow typically don't hit things. People who are driving really fast are more likely to run into things. Yeah, Garrett?
So like metals, right? They have a very, very high boiling point or melting point.
Yeah.
So if you were to superheat a steel beam to say like 200 degrees.
I don't think that would melt it, but anyway, go ahead.
But it would be hot
Yeah.
to the touch. But you had a bottom water boiling at 100 degrees, there would be more collisions happening in the metal than in the water?
No, it also has to do with the nature of the product.
Okay.
But the metal particles are going to be moving faster at 200 degrees than they were when they were cold.
Yes, but it's dependent upon
Right. It's not like, we raise this to 100 degrees and all the particles are moving the same. No. Some of them will be gas, some will be liquid, some will be, it's dependent upon the material. Good question. All right, so the higher the temperature, the more molecules are present with enough energy to react. Remember I said you had to hit the activation energy. When you put energy into the molecules and you raise their kinetic energy, more of them are going to have enough energy to react when they collide because you're inputting energy in. So not only are they moving faster, they also have a higher energy so that when they do hit with another particle, then they are moving fast enough to be able to collide. If two particles react and they are not moving quickly enough, they just bounce off each other. Nothing happens. They won't react. They have to have enough energy to break that energy of activation. Notice in the transition state here, you see that energy is being input from the collision, and also right here at the same time, we see that a new bond is forming and energy is being given off. This is all happening simultaneously, all at once. And then you have a product here at the end. Last slide for today. So orientation is the last thing that we talk about. This influences our reaction rate. This whole unit is about reaction rate. So molecules have to collide with the correct orientation in order to react. I think it's clear they call this the backside approach. But notice that bromine is attached on this side of the CH3. If the hydroxide hits in the correct spot, it can form its own bond and it will kick the bromine off. If the hydroxide is coming in from this side and hitting and bonking into the bromine, it will not kick the bromine off. So it has to have the correct orientation. Effective collisions are collisions that have both the proper orientation and they have enough energy. They have to have both things in order to have a reaction. So when we talk about reaction rate, and this is the math we're going to be doing here very shortly, this is the product of energy and orientation factors. So the energy factor is the number of collisions per unit of time with energy equal to or greater than the energy of activation. This unit of time is typically seconds. So how many times are the molecules colliding in a second with enough energy that is higher, is the same as energy of activation or greater than that? The second thing, this number is always a fraction or a decimal. It wants to know how many of those collisions have the proper orientation. Obviously, not all of them are going to collide properly, but what percentage or what fraction of them will. And that is what affects our reaction rate. And this is what we're going to be talking about, is the rate of reaction in this unit. Yay. So tomorrow we'll do math. All right, you guys got questions for me so far? All right, we're going to stop there. Yay. There's not that much left. We can do this tomorrow.